Seems like we did pretty well on the homework. So we'll have a review again today at 3:30. I'm in this room. And I'll just do it again and post it. Sorry about the delays for posting. Sometimes I don't get around to it quickly. Sometimes. So one comment on the homework. People did very well, I thought. There were some really good answers. I was really impressed. But there was one where a lot of people, not everybody, but struggled to find sort of this basis or the solution set to this equation. So if you look at this, I just want to give people another perspective on this, which is you can just take a matrix 1, 2, and just a 1 by n matrix, right? And then this is just a matrix equation. This is going to be a null space of this matrix equation. And you can kind of think, now that we have it, although we didn't have it last time, you can think about the rank nullity theorem. You can think of this matrix as being a linear transformation from Rn to R. In other words, if I call this matrix, think of multiplying by A, it's going to send Rn to R. It's a linear transformation. And the reason I'm saying that is that when you know, then you can look at this rank nullity theorem. This is an onto math, right? Because, I mean, if you just take E1, like the basis vector 1, 0, it goes to 1. Okay. So this is onto, which means its image has dimension 1. The rank nullity theorem says the null space dimension plus the dimension of the image, which is 1, equals the dimension of this guy, which is n. So that means that we should be getting, so that this should be n minus 1. The dimension of this should be n minus 1. Dimension of the space of solutions, which means when you're looking for that basis, you should be looking for n minus 1 vectors. So that's, I mean, I'm just trying to use something we just learned to say, you know, this can help you answer some questions qualitatively and say, okay, before I try to actually compute, how many vectors am I looking for here? This theorem gives you a way of doing that. And then once you do that, you can say, okay, well, let me find one solution. Right? Like, let me see if I can find one guy that will actually solve this equation. And I think it won't take you long to say, okay, well, if I take, you know, 2 in the first, -1, and then zeros everywhere else, that's a solution. And then you can kind of continue, kind of find a pattern. You get like n minus 1 of these. You can check if you want to prove it. Actually, the problem actually didn't say to prove that it's a basis, just so I accepted without explanation. But anyway, that's how I would approach that. Just wanted to share that. Try to help. Okay. I've been in like 2 administrative meetings in the last, well, I've been in many administrative meetings, but I've been at 2 administrative meetings in the last, I'd say 2 months, or a month, probably, maybe 2 weeks even, where it came up with like the insistence to abolish algebra as a part of the prerequisite for undergrads, like by other mathematicians. Which, you know, so I understand, like, it's very abstract what we're doing, right? And like a lot of people are like, well, you're not going to do math for a living. You want to go into something else. You want to use the things you learn in math. And I get that. And it's harder to make a case for algebra than it is to make for maybe like analysis or numerical analysis, numerical methods and so on. Nevertheless, there are many applications of group theory and of algebra in the sciences. And I think they're only going to grow. And I would also mention math is, totally useless until it's not totally useless, right? Like, at the advent of like quantum mechanics, Hilbert spaces or infinite dimensional vector spaces were totally useless. And then they weren't, because you could build a nuclear bomb, right? I mean, things started becoming a lot more important. So a lot of this stuff is, you should think, okay, well, we're going to try to get some of this deep abstract knowledge. And if we can use our creativity, we can find new applications for these ideas. I think that there's a lot of applications waiting to be found. So, but I did look into it a little bit, and the stuff we're about to learn on isometries and symmetry is very useful in chemistry, for example, and certainly in physics, but also in chemistry and understanding properties of molecules exhibiting certain symmetries. So I will try to make reference. I'm not a chemist, but I'll try to look into it a little bit and see if I can make reference to some of the applications as we go. It's not my specialty, but I want to keep algebra a lot. Love it. All right. So where we left last time is we were talking about orthonormal bases and orthonormal matrices. And we defined this group. We defined the group ON. As the group of orthonormal matrices. So that's matrices A. This is an n by n matrix, an n by n matrix. With A times its transpose is the identity. You want the transpose is the inverse. Now, there's another way of thinking about this. So this is very matrix, centered. In other words, we're looking at these as transformations of Rn. But I've tried to make the point that it's better to think of a vector space as just a vector space without a basis. And for that, if you define a metric on it, in other words, define this sort of dot product, whatever that is, on your space, then you can still define an orthogonal operator. So I'm just going to say V is a vector space. So there's a bit of stuff in Arden that we didn't cover, but I'm going to try to paraphrase what he's getting at with this other kind of approach or other perspective. It's the same stuff, but it's just a different perspective. So V is a vector space with a dot product. And the way you can think of this is you can think, well, in some basis, there is a way of writing vectors with a dot product, with the usual dot product. Okay, but you may not know what that dot product is. And you can denote it, so this is some map that takes, two vectors and returns a real number. This should be a real vector space. We'll denote it like V W. If I take a pair of vectors, I'll write it as dot product. So then a linear operator, remember an operator is just a linear transformation from V to itself, is orthogonal if when I take the dot product of T of V and T of W, I get the same as the dot product I had before. So here, this definition allows you to talk about orthogonal operators without talking about matrices. But again, if you chose the right basis, you could always just translate it into the more concrete matrix language if you want. We'll go back and forth. All right, so let's prove a couple of propositions about these operators. The one is this proposition 5.1.15. So this says that a linear operator on Rn, or we'll just say on V, it doesn't matter really, is orthogonal. Yeah, this should be n-dimensional. Sorry, I didn't say n-dimensional real vector space. And the n is just there to say that it's finite dimensional. I don't really care about n. Anyway, it's orthogonal if and only if for every vector t of v, or for every vector x, t of x dot t of x. This is saying that, okay, this is the definition of orthogonal. This is definition. And here in this definition, we had two vectors, v and w, and we took their dot product. But it's saying actually you just need a linear operator that preserves length. This sort of has length and angle in it. This just is saying you just need to preserve length. The proof is really elementary. So the proof is, well, certainly if it, I mean, one way is immediate, right? If it is an orthogonal linear operator, then just take v and w to be x, each of them to be x. So trivial in one direction. Try not to use that. Did I tell you guys that? So like there's some class. Also, I guess not a class. It's like a student of mine actually when I was at Northwestern. He was a graduate student, and he went and got a postdoc at Harvard. He told me we were at a conference. He told me an orientation for the graduate students there. They teach them, make a real point of it, he said, to like never use the word trivial when you're teaching, because it's like insult. It's like it makes them feel like they should obviously understand. That's, you know. So I'm not saying that story because I thought it was, you guys are tough. No, I'm not insulting you, right? It's not an insult. I just mean, yeah, right? Just take X for these two and we'll get that equation. So if it satisfies the. Okay, so let's assume that it preserves length. So it satisfies this equation. Then then you just do the following thing. You just take T of V. It doesn't really matter. You can take V minus or V plus. I'll do plus. Oh, it does. Pardon does. This should equal V plus W. Right, taking X for V plus W. That should be true. But we can expand both sides of this. So the point is this dot product is bilinear. Dot product is bilinear. Meaning it satisfies all the appropriate distributive properties. So I can write v dot v, and it's also commutative. I can write 2v dot w, w dot w. You can just expand it like I would an ordinary product. On the left-hand side, I need to use one thing, which is I need to use T as a linear operator. Being a linear operator means T of a sum is the sum of the T values of the vectors. So I can rewrite this way in both cases. And then do exactly what I did on the right-hand side to the left-hand side. Just T of B dot T of B plus 2 T of B dot T of W, T of W, T of W. Now, what we're assuming is that this equation is true for every vector x. So that means that equation is true for V. So I can cancel both sides here. That equation is true for W, so I can cancel both sides here. And of course, I'm in a real vector space, I can multiply by 1/2. And multiplying by 1/2 gives me TB dot TW is equal to V dot W. So it's an isometry in the, it's a linear isometry. All right. So that's a good thing to know, that you can only check length. Of course, this is sort of follows from, I think, your elementary school education, where you learn that, you know, two triangles are congruent if they have the same, you know, side lengths or something. All right. Another proposition which we'll use shortly, because I wanted to give a different, I do not like the proof. I want to mean theorems later. But this proposition helps us. A different proof. Right, so it says that a linear operator T on Rn, because it really should be a corollary, is orthogonal if and only if its matrix with respect. Is everyone okay with me doing that? With respect to? With respect to the standard basis. Is an orthogonal matrix. Is an orthogonal. And this is sort of saying what I was saying a moment ago, that, you know, there should be some basis that where it's an orthogonal matrix. But this is saying, okay, well, if you choose the standard basis, you've got Rn instead of V, then your linear. Remember, once you choose that basis, you can take any linear transformation or linear operator, turn it into something. And so the argument here is not hard. I'll just summarize it. It just says, okay, well, in this case, what is the fundamental property here? It's saying, well, let's say if A is the matrix, A is matrix, T set 2, that standard basis is 1 through En, then, well, we want AX dot AY equal X dot Y for all the column vectors X and Y. But this equation is just saying, how do we define it? We take the transpose and we multiply these matrices, should equal X transpose Y. And then the transpose is sort of anti-symmetric, so we can expand this out. We got X transpose A transpose T. X. And now the only thing so we can put this in parentheses, we get some matrix here. And so the question is, what matrices can we put in between any two X and Y and get this equation? The answer is only the identity. And the reason is the following. To check, that if B is any n by n matrix, Bij to n, and well, then I'll just say then. I take the jth column vector and take its transpose. Maybe I'll write it this way. Sorry, guys. Let me write it this way. Start with EI transpose B EJ. Take the ith standard basis vector, take its transpose, multiply B on the left with it, and then multiply on the right with EJ. You can check. This will be a 1 by 1 matrix. It will be just Bij. Matrix 1. What this does is it picks out the jth column of B. And what this does is it will take the ith j column. So in particular, if this is true for all x and y, it's true for all EI and EJ. So we had EI transpose B EJ equals EI transpose EJ, then B has to be the identity. Because if I and J are not equal, these are orthogonal vectors, so we get 0. And if I and J are equal, you get 1. So that shows, oh, sorry. That shows this. A transpose A. We're done. All right. Let's do a little more concrete stuff. Let's see what these groups are in the cases in some low dimensions. Let me summarize this theorem. 5.126. It describes O2. So if R is an SO2, everyone remember what that means? It's an orthogonal matrix with determinant 1. By the way, let me ask you this, guys. Why are the determinants of orthogonal matrices only plus or minus 1? Why can't it be 17? All right, what do you think? Any takers? Not 1 over. Determinant of, you're on to something though. Determinant of transpose is what? Of a matrix? It's just the determinant. But I know what you're getting at. You're saying that if it's orthogonal, it must be the inverse. Maybe that's what you meant, Kale. Right.
Yeah,
so
like the determinant of A times B is
right.
So
determinant of 1 is what you're saying is determinant of 1 of the identity is 1. It's determinant of A transpose times A, because A transpose A with identity, which equals the determinant of A transpose times determinant of A because of the multiplicative property of determinants. But this is the same as the determinant of A squared. So the determinant of A is square has to be 1. only two numbers with that property. Good. So we have plus or minus 1. If it's minus 1, oh, if, sorry. Okay, let me just write that. Let me do this. Oh, and that's this minus 1. And this. All right, and he makes other words, but I'm going to skip the other words. So what's the proof of this? Well, I'll say the other words, but I won't. Proof is really not hard. Because we had this result last time, it told us about orthogonal matrices and what they were. If I have a, remember last time we said if we have an orthogonal matrix and we look at the columns, the only way it's an orthogonal matrix is if this column, if these columns have a normal basis. Last time. It's in ON, if and only if B1 through Bn is an orthonormal basis. So now we're in R2. And we're back, we're home finally, right? This craziness, and now we're back in the world of familiar Cartesian plane. So what does it mean? So now I just have a V, so I'm looking for V1, V2, and I want them to be orthonormal. So the first part to pay attention to is the normal part. Normal vectors are unit length. So just take our unit circle. And to get a V1, we just need to choose something on the unit circle. So do so. Choose something. This is going to be our V1. Of course, we have a parametrization of the unit circle with cosine sine. So we can start to write down our matrix cosine theta, sine theta. And we know our second vector in our column will be also on the unit circle. So it has to be somewhere else at the normal property. But we also need it to be orthogonal. And for it to be orthogonal, well, you can think this has to be on a line perpendicular to this line. And the lines perpendicular to this line will have negative the reciprocal slope. Right? You have two lines and they're perpendicular, you take negative the reciprocal. So the slope of this line, of course, is slope. Whoa, slope is tangent. It's cosine, yep. Sine over cosine is tangent. Remember. Right. So that we should get a negative cotangent as our negative reciprocal. And of course, there's only two guys that will do the job there, right? There's only two guys here, and they're going to, we can either have sine, theta minus cosine, or we could put a minus here. And this. Now, so those are the only ways we can get an orthogonal matrix. So these are the two options here. And this option, you can take determinant, you can see that you get cosine squared minus negative sine squared. Or cosine squared plus sine squared. So this has determinant 1. Whereas the other option, we would see that we get negative 1 determinant. So since these are the only two options, these are all of the possible 2x2 orthogonal matrices. Now, in this first case, the way you can see this, if I take any vector here, and you can justify this, but I don't want to spend much longer on this particular case. If I take any vector, green vector, some point, W, and you apply this transformation, you'll see that what this so in other words, I apply this matrix to W. So W has some coordinates. I can think of it as a vector AB. And I call this A, and I look at A times W, I'll get some other vector. What that other vector is it's W, but I attain W by rotating by an angle of theta, counterclockwise. You can check that by looking at essentially sort of the polar form, of W, and using the addition formulas for sine this. See that this is precise. This A of W will be rotation of the origin. So this gives us a way of computationally rotating the plane. Multiply by this matrix. This guy is a composition of two things. It's a composition of a rotation and a reflection. The other thing we can do linearly at the origin is we can, that's not a rotation, we can reflect. So this is a rotation plus reflection. And SO2, that's all it is. Rotations, reflections, and combinations thereof. But everything is of that form. SO2. So not get through everything I want, but people did ask to get a little bit. So let me tell you a little bit. Three-dimensional case. This, of course, is very useful if you were, I don't know, programming a self-driving car or something. I don't know, like if you wanted to actually have the transformations of that we work in real space. Of course, these guys, these are 3 by, if you look at them as give them coordinates, these are going to be 3 by 3 matrices. So we have 9 entries, 9 numbers that come into play. Yeah.
What's the symbol up there?
I'm sorry?
What is the symbol?
Oh, it's like a backwards. It's just being sloppy. Sorry. Ignore it.
Oh,
Completely. Yeah, it consists of 3 by 3 matrices of a special type of this that satisfy this equation. So, but that's 9 numbers, right? For any given kind of rotation or whatever the plane that you may want, or the three-dimensional space that you want. That's too much information. Too much. We should really only need 4. That's what I want to say. Well, that's what Euler tells us. Euler had a really a good hand in this in understanding symmetries in 3-dimensional space. As he had, the guy was insane. He published a ton. He was like went blind and he kept on like dictate math to his grandchildren. Right? I have some good grandchildren to do that. You only need 4, right? You should only need 4. Here, we only needed 1 param thing. Like for SO2. We just need 1 param. Let's say, okay, we're rotating this much counterclockwise. What are the 4 parameters you think you should need? Really only, let me correct that. You only need 3, but it looks like. What are the 3 parameters you need? Who can tell me? I'm going to rotate in 3-dimensional space.
How much you rotate the X? How much
Okay,
you rotate
how much?
Y,
I
how
need
much
an
you
angle.
rotate Z?
Oh, no, rotate. See, that's, I hate your physics, aren't you? No, okay, someone does this. Right, this rho theta. I don't understand this. The moments of inertia. Crazy stuff. What does that even mean? No, yeah, like how much can you rotate in the various, what do you mean? What's going on? If I rotate, no, you're right, they do this, it's possible. Yeah, but projections of rotations aren't really rotations. I mean, they're kind of different. Right. I mean, such things exist, and there's interpretations. But what does that mean? Like if you're rotating, like let's say I'm standing, I'm like floating in space and I start to rotate. What do I need? You need to kind of like know where your like head is pointing versus your legs. You need like the axis of rotation. You know the axis of rotation, you've got your right hand rule, you kind of can, and you've got an angle, you can say, okay, I'm rotating this much about the axis of rotation. So how do you get an axis? Well, an axis is a line through the origin, right? Everything's fixing the origin. A line through the origin. And how do you know what a line is? Like how can you describe a line in three-dimensional space? What parameters do you? Your answer is fine. I'm just stubborn. I have a sphere and I choose a point on the sphere. I can get a line. That tells me everything I need to know about a line. I've got a little redundancy because I could take the antipodal point, the opposite. Right. But if I take a point on the sphere, which is two-dimensional, then I'm good. So I take a point on the sphere, I draw a line through the origin and through that point. The origin will be here. This is going to give me my axis of rotation. I'm going to take that point that I chose. Take that point that I chose, and I'm going to give it coordinates. I don't know why I'm giving it blue coordinates, but okay. Give it coordinates A, B, C. This is the point. This is a point on the sphere, so it has to satisfy the unit sphere. The unit sphere, namely, this point has to satisfy a squared plus b squared plus c squared equals 1. That's the axis I want to rotate by, and then I want to rotate by angle of theta, counterclockwise, right-hand rule. If I'm using right-hand rule, I should really take the point on this. I want the direction. All right. So this is all you need to write down the matrix. However, the matrix is ugly if you have this information, but there's something that's pretty. Done by Hamilton. They're called the quaternions. So you guys know about complex numbers. A plus I squared equals -1. You can do all your arithmetic with complex numbers, just using I squared equals -1. So Hamilton was drunk one day, or evening, I don't know the time of day, but the story goes, he was drunk. He realized he could extend this notion of complex numbers to 4 dimensions. Very excited about it in his inebriated state. And he went to a bridge, Ireland, carved in the relations, the quaternions into this bridge. So the story goes. As a first division, like authentic, what we call a division algebra. He realized that in order for this to make any kind of real sense, you had to add a wrinkle. which is you had to have these be non-commuting. But you could define relations like this. And if you define all of these relations and you do algebra in the normal way, making sure to be sensitive to commutativity, then you get a nice arithmetic number system of quaternions. This is denoted. The thing about this is that this is sort of the complex part, if you will, of the quaternion, and this is the real part. I shouldn't have used A, B, and C up here. A different A, B, and C. That can correct, because sorry guys, it's called X, Y, Z. What I can do in this thing, my theta, is I can write down a single quaternion. Cosine of theta over 2, a sine of theta over 2, times quantity xi plus yj plus zk. I'll call this rho theta. And xyz. I'll just call it, I might give this point a name. Let's call this point P. All right. But we'll think of it as a vector. We'll call it P. Rho theta P. This is so in the quaternions, you can do everything you want to do, which is amazing. Remember fields? We could do everything we want to do in a field. We could add things. We had additive inverses. We had a group there. All non-zero guys had multiplicative inverses. The same is true for quaternions, except it's non-commutative. It's the only difference, the only thing keeping quaternions from being a field is that it's not a commutative multiplication. That's it. Everything else it has. It's great. It's lovely. But now if I take any other number or any other vector, x tilde, y tilde, z tilde, I can form this kind of imaginary quaternion bit. And I can multiply in the quaternions. If I do that, I take this and I multiply on the right by this guy, and I multiply on the left by its inverse, which has a very simple formula. This is the rotated so point being, what's the why care? Why do you care? I don't know if you care, but what you can do with this is you can go down from those 9 entries in that 3x3 matrix that you had to write down to 4 entries in a quaternion vector, which are totally determined by the geometric information you want as your input for your rotation. So you want to know the axis of rotation, you can write that down. You want to know how much you're rotating, you can write that down. And you can write this down, and this is the formula for rotating the actual vector. Computers do this. Like I think a lot of gaming programs use this instead of 3x3 matrices, just to have efficiency. So anyway, here's some quaternions. They're really interesting. I mean, they're useful in other areas of math, of course, besides just transformations. But it's, yeah. Anyway, very good. One thing you might notice about this, although it's kind of hard to notice, is that if you look, you've got 4 coordinates. You've got the real coordinate, and you've got these other 3. And so you're in actually 4-dimensional space. And if you look at these particular coordinates, you'll see they satisfy an equation, which is the equation for a sphere, namely a squared plus b squared plus c squared plus d squared equals 1. That's a three-dimensional sphere, meaning it's like a sphere in three-dimensional space is two-dimensional. It's like the boundary, right? So the boundary, when I say sphere, I mean the boundary. So our usual sphere that we are used to looking at is two-dimensional. This is a three-dimensional sphere, and SO3 actually has the shape, almost the shape of a sphere, a three-dimensional sphere, but not quite, because actually you identify this with its negative in SO3. In other words, I could have chosen negative. It would have made a difference. There's another group that is actually the three called SU2. Very, very important in physics, especially unitary. All right. So fantastic stuff. I apologize deeply for all the things I've said. So now we want to go on and really talk about chapter 6, about symmetries and isometries. So chapter 6.1 is pictures. So please do just look at the section. You can look over the actual, like rather than just the problems, like look at the actual section. It talks about like, okay, here's a figure. We want to study, symmetries of this figure. What can we do to this, to the ambient space around it, or to it itself, that will preserve the shape, right? So if I have a cube, I can rotate it 90 degrees, right? And I'll still have a cube. It'll be the same exact shape, but I've done something to it. So those are our isometries of a particular shape. So this is, I'm going to just say, you should read over this section. And 6.2, they start talking about isometries of Rn. And this is not very far from what we've just been doing. There's one kind of result I want to state and take a quick look at, and so what is an isometry of Rn? It's a definition. A map T from Rn to Rn is an isometry if T of V minus T of U 2. We call it phi. I'm sorry, I shouldn't call it T. We call it phi. T makes it look like it's a linear map. It's not. It's just a map that preserves distances. Now you might say, well, didn't we just study that? Isn't that just an orthogonal transformation? The only difference is I'm not insisting that this is linear. It may not be linear. So one nonlinear, not very linear, isometry would be just translation. And I can take a plane and I can translate it. Why is that not linear? Well, linear transformations take the origin to the origin, take the additive identity to itself. So if you translate, you move 0 away from itself. That's not linear. It's not very, well, it certainly looks linear. I mean, it sends lines to lines, but in that sense, it's not a linear transformation. So we want to study these isometries, and let me just state the theorem, and I'll have to wait till next time to prove it, I think. So this is theorem 6.23. And this gives us characterizations of all the isometries of Rn. The following conditions are equivalent. On map, conditions on descending Rn to Rn. equivalent. One is that it's an isometry. Two is that it preserves the dot product. Two vectors. Three, sorry, it's not just an isometry, pardon me. Phi is an isometry preserving the origin. That's phi of 0 equals 0. And then the third is that phi is an orthogonal operator. Now, when you first look at this, I would not fault you at all to say, well, this is, silly. Why are you saying, didn't we just define things this way? However, there is something missing here, right? So there is something to prove here. So certainly if it's an isometry preserving the origin, we can prove this pretty quickly. But why isn't this obvious? Why isn't it, if this is true, isn't this what we used to define an orthogonal operator? Not quite. We said that an orthogonal operator by definition is a linear operator that satisfies this. So what you need to show to go from here to here is that phi is linear. You don't have that yet, linear transformation. So Arden has a proof that I don't like, apparently given by one of his students. So I'll give a proof I like, but you can read it and tell me which one is better.